There's a specialized strategy of proof which is called induction. And I want to go over it. It's the trickiest one. It's very unusual compared to all the others. You use induction when you're trying to prove, or you might use induction when you're trying to prove a whole sequence of related statements and that they're all true. Infinitely many statements. And I'll say what the strategy is, but it makes more sense once you get into the examples. So, but the strategy is first you prove the first statement is true, however you need to, a direct proof usually, or whatever it takes. You just prove that first statement. Then what you do is you assume that the kth statement is true. And what I mean by that is any one of the others, any statement, you're just calling it generically the kth statement. And you're going to use that to prove the next one, the k plus 1th statement. So you're basically showing how each statement can be used to prove the next one. Generically, you're not committing to any particular, like you're not proving that the third one gives you the fourth one, or that the 19th one gives you the 20th one. You're not doing that specifically. You're doing them all at once. You're saying any one of them, I can show you how that can be used to prove the next one. So it's important that you leave k as a variable there, as an undetermined number. You don't commit to a particular number. It has to be generic. All right. Yeah, it's weird. Let me show you how it works. So a classic induction proof is to prove that the sum of the first n integers is given by this answer. So like if you wanted to add up the first 10 numbers, 1 plus 2 plus 3 all the way up to 10, you could do that one by one, right? Or this formula will give it to you. It'll be 10 times 10 plus 1, 11 over 2. So 55. And you can check that that's true. It's easy to prove that any one of them is true because you just work it out, but we want to prove it's true for all of them, infinitely many. It's true for the first one integer, it's true for the first two integers, the first three integers, and so on forever. All right, so as the strategy above says, the first thing you do is you're supposed to prove that the first statement is true. Well, the first statement is the sum of the first one integer. Well, that would just be 1. There's not even a sum to be done. It's just one number. 1, let me do this in math mode, 1 equals. And is it true that this formula gives you the same answer when you plug 1 in? 1 times 1 plus 1 over 2. Yeah, that equals 1. So it works. So that was just a very simple and just kind of a verification to prove the first statement. All right, but now suppose that the sum of the first k integers, 1 plus 2 plus 3 plus, does equal this formula with a k plugged in. All right. We will show, now usually we don't write what we're going to show, we just go ahead and do it, but I want to be clear here. What we want to prove is that 1 plus 2 plus 3 plus, if we add up the k plus 1 numbers, that one works as well with a k plus 1 plugged in. All right. So we're going to use this to prove this. And if we can do that, we will be done. Because again, if we can do that, then we are showing how the kth statement can be used to get the k plus first statement. And let me just follow that logic through. Since we already did the first one, then this will say, well, since the first one is true, the second one is true. So the second one will be true. And then since the second one is true, the third one is true. And since the third one is true, the fourth one is true, and so on. Right? So since we generically prove that each one automatically gives you the next one, I always liken it to a line of dominoes, right? If you knock the first domino down, and then you prove that each domino will hit the next domino, then you knock all the dominoes down, right? So that's what we're doing. But we have to do that. We have to get from here to here. So normally I wouldn't write this. This is just so we know what our target is. But now let's get to it. Well, I'll just do this directly, and I'll start with this, and I'll try to turn it into the formula. Okay. Well, right off the bat, I know that I have to use my little hypothesis here. This is called the induction hypothesis. The case statement we're allowed to assume is true. We get to assume that and use it to do the k+1 statement. Well, the cool thing is I have 1 through k being added up. We just have an extra term now. And I know 1 through k added up equals this. So I can replace 1 plus 2 plus 3 plus ... plus k with k+1 over 2. Oops. But we still have that k+1. We have that leftover term right here. That's still there as well. All right. And now let's see if we can turn that. Remember, we're trying to turn this into this formula, and let's see if we can do it. Well, let's see. I am going to get a common denominator, I think. So I guess I have to do like that. Common denominator equals, and now I can put them together. One fraction with a 2 in the denominator, and I have k+1 plus 2k+1. And is that going to equal this? I have the 2 in the denominator. Now I just need... So yeah, I think both of these terms have a k+1 in them, so I can... went on to another line. I can factor out the k+1. And what does that leave? That leaves a k, and it leaves a 2. Which is equal to k+1, k+1 plus 1. Which is our formula with a k+1 plugged in. If I put a period. Okay, yeah. So this is an example of the math, even when it's an inline statement, it went over. I can't fit this all onto one line. There are things you can do about it, but that's not the point of this video, so I'll just leave it like that. Okay, so what I said we were going to show, we showed. We got from there to there. Got from there to there. We used our induction hypothesis along the way, in fact, right at the beginning. Therefore, I can say 1 plus 2 plus 3 plus ... plus n equals n plus 1 over 2 for all integers n. I knocked all the dominoes down. Okay. All right, let's do another example that has a different feel to it, but it'll still be induction. For every integer n greater than or equal to 4, n factorial is bigger than 2 to the n. So 4 factorial is bigger than 2 to the 4, 5 factorial is more than 2 to the 5, 100 factorial is more than 2 to the 100. They're both big numbers, but we're saying that the factorial one is always bigger from 4 on. All right. So first we have to prove the first statement, which is starting at 4. We want to prove that 4 factorial is bigger than 2 to the 4. Well, 4 factorial is 4 times 3 times 2, which is 24, and 2 to the 4 is 16. So 4 factorial is bigger than 2 to the 4. By the way, I guess it's not true for 3, which is why we're not claiming it's true for 3. 3 factorial is 6, but 2 to the third is 8. So yeah, it wouldn't be true for 3. Okay, But our base case, our first statement, which is the n equals 4 case, worked. Now suppose it's true for k, where k could be anything. Prove that k, it's not prove, excuse me, suppose k factorial, suppose we knew k factorial was bigger than 2 to the k. We will show that, we're going to use that to show that k plus 1 factorial is bigger than 2 to the k plus 1. So again, typically you don't say what you're going to show in a proof. Sometimes you can. I shouldn't say you typically don't. Sometimes you do. If you think it would help your audience to know what you're in the middle of, that's fine. So let's try it. So let's start with k plus 1 factorial. Let me just put a space in there so it's not centered right off the bat. All right, so k plus 1 factorial. Now immediately I would like to use the fact that k factorial is bigger than 2 to the k. But I have k plus 1 factorial. I don't see a k factorial. But sort of like in the summation problem, the first example we did, this is kind of hidden inside that, right? K plus 1 factorial is all the numbers from 1 to k plus 1 multiplied up. Well, that includes all the numbers from 1 to k, just includes one more number, k plus 1. So I could write that this is k factorial, but then times k plus 1, right? It's 1 through k, and then k plus 1. Now I know k factorial is bigger than 2 to the k, so k factorial times k plus 1 is bigger than 2 to the k times k plus 1. All right. So far so good. I got a 2 to the k times k plus 1. Now I need it to be 2 to the k plus 1. Well, so 2 to the k plus 1 is k plus 1 2's. This is k 2's being multiplied. If this were a 2, I'd be set, right? If it was 2 to the k times 2, I'd be set. Now k plus 1 is not 2. However, k plus 1 is certainly bigger than 2, right? K is 4 or higher. So it's bigger than 2 to the k times 2. So I have some flexibility here because it's an inequality. I don't have to make everything be equals like I did in the previous example. This one I just need to have a string of equals or greater thans, and I'm fine. Yeah, so that equals 2 to the k plus 1, and I've done it. Ignoring the middle stuff, I've proven that k plus 1 factorial is bigger than 2 to the k plus 1. Therefore, n factorial is bigger than 2 to the n for every integer n that's at least 4. Okay. So those are two examples that use induction, and it's a different way of thinking. You're not proving this directly. You're thinking of it as a bunch of statements for 4, 5, 6, 7, 8, and you're showing that each one kind of recursively gives you the next one. Sometimes a statement could be proven with induction, but it could also be proven directly, and usually the direct proof would be easier, and you would prefer that. But sometimes, like in both of these cases, a direct proof is not really feasible, and so you need to do it using induction. Okay.